Let's talk about an example of a task that can be designed as an episodic task or as a continuing task. So this problem is about the inverted pendulum. So the idea here is that this car should move left or right to avoid this pole to fall down. So we need to balance this pole using just this car. So if we want to implement a reinforcement learning algorithm to solve this, we can design the algorithm as an episodic task. If we consider that as an episodic task, then the reward could be, for example, to give a +1 for each step, for each movement that we make with the car before failure. So if we can make more movements of the car before the pole falls down, then we will have more rewards. Otherwise, we will get less rewards. And remember, we want to maximize the reward. So in this case, the return will be the number of steps before failure. Now, if you want to implement this solution, this reinforcement learning solution as a continuing task, then you can consider, or you need to consider a discounted return. And in this case, the reward could be, for example, -1 upon failure and 0, reward 0 otherwise. Okay, so the agent will be making movements where it will have 0 as a reward every time it keeps, or every time step it keeps the pole balanced. And when the agent make a failure, then it will receive a -1. So in this way, the return will be defined as minus gamma to the k, where k is the number of steps before failure. In either case, return is maximized by avoiding failure for as long as possible. So these are two examples in which you can implement a solution for this pole balancing problem. This is a very famous problem when you are studying control. And of course, these are only two possibilities. There are many ways in which you can implement and solve this problem using reinforcement learning. Another example is the car on the hill problem. In this problem, we suppose that we have a car, and this car doesn't have enough power in the engine to just go forward to get on top of the hill, the top of the hill. So we need to go backward and forward many times until the car gathers the speed to go up to the hill. So to solve this problem as a reinforcement learning problem, you can assign, for example, a reward of -1 for each step where the car is not yet at the top of the hill. And in this case, the return will be then the negative, the minus of the number of steps before reaching top of the hill. The return is maximized by minimizing the number of steps needed to reach the top of the hill. This is actually a very interesting problem to analyze and to play with using reinforcement learning algorithms. This is it might seem to be a trivial problem, but it's not a trivial problem actually. Many control algorithms, classical control algorithms, have problems here because to solve this problem you first need to go away from the goal, and this is something not considered in many classical control algorithms. But in the case of reinforcement learning, since we need to explore and interact with the environment, this is a very well suited problem for our reinforcement learning approach. We need then a unified notation to solve episodic and continuing task problems. So in episodic task, we number the time steps of each episode starting from 0. We usually do not have this to distinguish between episodes, so we write st instead of st, j. So during the training of the algorithms, we just take care about the time step. We don't care if that state was perceived in episode 1 or episode 5. We don't care about that, so that's why we just have an index for the time step. And you need to think of each episode as ending in an absorbing state. So this square state will represent an absorbing state, a terminal state, where once the agent enters this state, all the rewards following will be 0, and the agent cannot go out of this until you reinitialize a new episode. So by assuming this, we can cover all the cases, and we will need to write the return, the expected return, as the sum from 0 to infinity of the discounted rewards. So in general, you will see that the learning algorithms in reinforcement learning will consider always this gamma here. So what you can do, if you can make sure that this is going to have a terminal state, you can simplify gamma by making it 1. If not, you can usually consider this to be a number between 0 and 1, like 0.1 or 0.2. As it says here, where gamma can be 1 only if a 0 reward absorbing state is always reached. To avoid, we have here an infinite in the return. The Markov property is a very important one when we talk about reinforcement learning. In the Markov property, we mean that the state at step t should contain all the information needed by the agent in order to make a best decision, the best next action to be performed. So by the state at step t, the book means whatever information is available to the agent at that time step, information about the environment. This state can include immediate sensations, highly processed sensations, as we said before, could be low level, high level, and structures built up over time from sequences of sensations. Ideally, a state should summarize past sensations so as to retain all essential information. It should have the Markov property. So mathematically speaking, we define the Markov property. We say that the environment has the Markov property if the probability that the next state and the next reward, given the whole history of transitions of states and actions since the very initial state is 0 up to the current state t, that if this probability is the same as the probability of knowing only the current state and action, then we say that the environment has the Markov property. So it means that if the environment has a Markov property, we don't need to know the whole history of transitions from the start state to the current state. We just need to know the current state, current action. So this probability here and this probability here will be the same in a Markov property, in an environment with the Markov property. If a reinforcement learning task has the Markov property, then we will say that we are talking about a Markov decision process, an MDP. If state and action sets are finite, it is a finite MDP. So here we will be talking mainly about finite state spaces and finite action sets, but these methods can generalize, making changes, of course, to problems with infinite number of states and infinite number of actions. To define a finite MDP, you need to give the sets of states and actions that the agent will perceive and the actions that the agent will have available to be executed. You need to define optionally, this is something that you could have in a problem or not, is the transition probabilities, which is a probability distribution that will tell you, given that the agent is in the state S and it performs action A, the probability that the environment will transition to some next state S prime. So for some problems we have these probabilities, these transition probabilities, and this is what we call a model of the environment. But in the most challenging problems we don't have this. That's why I said you can define this optionally. If you have it, you can use it and you should use it. But in the most challenging problems you don't have this. When you have this model, we say we are talking about model-based reinforcement learning. When we don't have this, we are talking about a model-free reinforcement learning. And finally, and this is something that you need to have always, is the reward function, the reward probabilities. And as we are writing here is the reward that you will get if you go from state S to a state S prime by applying action A. Okay, so it is the expected reward that you will get in the next time step if you are currently in some state S. The action that you perform is action A, and the next state is the state S prime. So